Okay. And the next speaker is Shivani Bhandari. She is an invited online speaker. She is going to talk about the host galaxies and local environments of our solid Earth. So Shivani, please start when you get ready. So let's welcome the next speaker. Sorry.
Hi, can you hear me?
Yes.
Okay, and my slides are looking okay?
Yes, looks perfect. So please start.
Okay. A very good evening, everyone. I am Shivani Bhandari, and I'm working at Astron Jive in the Netherlands. I'm very thankful to the organizers, first of all, for giving me an opportunity to talk to you today about FRB host galaxies and their local environments. So the majority of the work that I will present today was done in close collaboration with the F4 and Craft teams. So I will start off, can you see the next slide? Yeah, there's some lag, I guess, but it's there.
Yes, it's changed.
So
yes.
Okay. So I will start with showing the transient phase space plot here. Here, x-axis, to annotate, okay. So I think someone is annotating now. I don't know. Okay, anyways, I'll continue. Here the x-axis presents the product of the time duration and the frequency, and the y-axis represents the luminosity. The brightness temperature of 10 to the power 12 Kelvin serve as a boundary between the processes which are generated by coherent and incoherent mechanisms. And as you can spot here, FRBs lie in the top part of this plot. They are millisecond duration, extremely energetic extragalactic transients. So when we zoom on FRBs, we can see that their luminosity here vary by 6 orders of magnitude. Also, the detection of the fast radio burst from the SGR 1935 in our galaxy is definitely bridging the energy gap between the galactic sources and extragalactic bursts. So it is becoming more likely that magnetars could produce a subpopulation of the FRBs that we observe today. So with the current observational evidence, what can we say about their physical mechanism and progenitors? So broadly, the coherent radio emission models can be grouped into 2 categories. So first are the one which invoke the magnetosphere of the compact objects, and other one invoking the relativistic shocks which are occurring far outside the magnetosphere. So the current model also predicts that the FRBs can either be caused by catastrophic or rare events, or rare collisions between old neutron star and white dwarfs, for example, in which case they are very energetic and we see them as one-off events. And on the other side, they can be more common periodic bursts of flares from young and rapidly spinning neutron stars, such as pulsars, in which case they can be less energetic and repeatable. So the table here lists all these types of models which are proposed. Okay, but the most straightforward way to find what produces a burst is to pinpoint its location and study their host galaxies. Thus, the host identification became the most urgent observational priority for FRB science, and that's exactly what is being done in the community at the moment. So here I show the gallery of some of the FRB host galaxies that are localized by the Australian Square Kilometre Pathfinder Array in Australia. And as you see, majority of the FRBs that ASCAP finds and have localized are non-repeating at the moment. This is the plot of the host redshift distribution for 20 or so FRBs. And you can see that most of the FRB hosts are now localized below a redshift of 0.5. However, there is one burst which is localized at a redshift of 1, which I will discuss in more detail in the later presentation. So we can ask 2 questions to investigate the FRB progenitors. Firstly, what are the local environments of FRB host galaxies? And the other is what are the galactic scale properties of the FRB host looks like. So first we will explore how FRBs are tracing their local environments. Now, because of the repeating nature of some of the FRBs, very long baseline interferometry or VLBI observations have allowed them to be precisely localized with milli-arcsecond level precision. And such observations and such precise localizations have enabled the studies of their local environment. So, as everyone know here, repeating FRB R1 was the first one to be localized. And this burst came from a tiny, low metallicity, highly star-forming dwarf galaxy at a redshift of 0.1. Radio observations also revealed the presence of a persistent radio source, which we now call as PRS, and that was found to be co-located with the burst itself. Precise VLBI observations were in fact able to constrain the size of this PRS to be less than 0.7 parsec. So these observations showed that the burst is either associated with a low luminosity AGN, or it could be a neutron star energizing a supernova remnant or a pulsar wing nebula. This FRB had an extremely high rotation measure, and such a high RM value has only been reported for the galactic magnetar living inside near the galactic center. So what does this tell us? So the presence of the radio nebula and the very high rotation measure of the FRB led to a concordance picture where FRB is a flaring magnetar and it is embedded in a magnetized wind nebula, and this magnetar can be formed as a remnant from different channels such as superluminous supernovas and long GRBs, because those explosions, those channels of magnetar formation happen mostly in the dwarf galaxies. Next is a very recent result about another active repeating FRB, which was discovered by FAST and localized by the VLA Real Fast team. The dispersion measure of this burst is high, it's about 1200 DM units, but strikingly the host galaxy of this FRB is a dwarf at a redshift of only 0.2, which leaves a total of about 900 extra DM units that would come from the host galaxy itself. And this is about 5 times higher than what we have seen for an average FRB host galaxy. Moreover, like its twin brother R1, which is FRB 121102, this burst also has a PRS, and this burst properties, if you look at the polarization properties again, the RM and rotation measure is very high and it's very variable as well. So these two FRBs, which are linked with the PRS, are among the most active sources, which could imply that these may be the characteristics of young and active FRB sources surrounded by dense and magnetized plasma. And while the very first repeating FRB R1 came from a dwarf galaxy, the second repeating FRB source originated from a star-forming knot in a nearby massive spiral galaxy. So it was a completely different type of galaxy. And for this case, there were no PRS and no extreme magnetic fields were observed. And interestingly, this FRB was also detected by low FAR, so down to a frequency of 110 megahertz. And this low frequency detection implied a much cleaner FRB source environment. And thanks to the precise localization using the VLBI and the European VLBI network and the high spatial resolution studies from the Hubble telescope, the burst was found to be offset from this star-forming region. Now this had a direct consequence on the age of the progenitor, which was found to be more compatible with that of high-mass X-ray binaries than young magnetars. Another actively repeating FRB was from CHIME, and this burst was followed up by so many interferometers. The plot here shows the localization of this source to a massive star-forming dusty galaxy. The host was found to be dominated by an old stellar population, which suggested progenitor scenarios which have longer delay times. GMRT and VLA initially reported a PRS that could be associated with this burst, and these are the dot dashed circle in the image you see here. This is a very recent image from the, sorry, yeah, so this is a recent image at 22 gigahertz. And you can see that the radio emission here is consistent with the VLBI position, but the emission turned out to be resolved at VLBI scale, suggesting evidence of diffuse radio emission due to the star formation than any compact radio source. So far, repeating FRBs were either localized to dwarf galaxies, or they were coming from close to star-forming region in massive galaxies. However, recently, the CHIME FRB was localized to a globular cluster in a massive M81 galaxy. This was a jaw-dropping discovery, suggesting that FRB local environments can be very diverse than what we originally thought. The older stellar population in the globular clusters suggest a progenitor environment, which may have been formed by channels such as accretion-induced collapse of a white dwarf or a merger of compact stars in the binary systems. So moving forward, as far as the hosts of non-repeating FRBs are concerned, this is a high resolution view of a sample of FRB host environment using the Hubble Space Telescope. Here the blue shows the UV light and the infrared observations are shown in red, and black ellipsis shows the position of the FRB with the uncertainty. And we can see that majority of the bursts are offset from their host galaxy centers, and the hosts are here a mix of either spiral galaxies or more lenticular systems. And you can notice here sometimes that FRBs are also coming from the spiral arms of their host galaxies. Another thing to note is that FRBs are not originating from the regions of elevated local star formation in comparison to the mean value for their host. So out of this sample, there were 3 FRBs that had a detected radio emission, which was attributed mostly due to star formation. So again, there is no persistent radio source for these sources. Talking about specific burst, a very recent result from ASCAP is that it has localized a non-repeating FRB to a complex host system at Z equals to 1, which is here, as you see in the spectrum, confirmed by the origin lines in the host spectrum. Here, the second row of plots shows the host galaxy in different bands from the very large telescope. The presence of 2 bright clumps A and C, and then there is this diffuse feature B between them, is suggestive that these galaxies might be interacting or merging, but they are at the same redshift. And the white ellipse here shows just the apertures for the telescope used for each clumps. In this second panel here, the black ellipse here shows the 1 sigma FRB localization region, and the prospector SED modeling for the host tells us that the host galaxy is massive and has a little star formation of about 0.4 solar masses per year. Interestingly, for this burst, after accounting for the Milky Way contribution in the DM budget, we find an excess in the extragalactic contribution to the DM, and this is by knowing the median expectation from the DMZ. So when we subtract that off, we see an excess host DM contribution, which is about 1300 in the host frame, which is, I think, the highest of what we have seen so far. So the absence of strong Faraday rotation, I should have said that the Rn for this FRB is not very high. So the absence of strong strong rotation, Faraday rotation, is suggesting that whatever is causing this excess dispersion, it is originating in a less magnetic plasma. So it could be the ISM of the host galaxy. So not because the plasma or the vicinity of the FRB is not as crowded as what we have seen for, let's say, FRBs who are living in a dwarf galaxies with a PRS source. Yeah, so that was the very first FRB localized at redshift greater than 1. So moving forward, FRB 210117 is another recently published burst. And the main thing about this burst is that this is the only FRB found in a dwarf galaxy where the repeating nature has not been established. Otherwise, in other words, this is a non-repeating burst coming from a dwarf galaxies. And interestingly, the dwarf host of this burst is also very different from those of repeating FRBs in terms of its very little star formation rate. And unlike the other active repeating FRBs that live in dwarf galaxies and have a PRS, we do not find any PRS or any radio emission coming from this FRB host. Now, this low magnetized environment, so this FRB has an RM of about 43. So the low magnetized environment and the lack of a PRS again indicate that this FRB source could be older than those which are found in dwarf galaxies, and therefore it sort of establishes the diversity of FRB sources that we are seeing in dwarf galaxy environments. Like they are not always not the one which have PRS or high rotation measure, and this burst is clearly an example of that. I will quickly mention this new burst FRB 220319D, which is discovered and localized by the DSA team. This FRB is coming from a star-forming spiral galaxy, which is just 50 megaparsec away, so just around the corner. The DM of this burst is somewhat lower than what is predicted from the galactic models for the Milky Way. And the authors also show that there could be significant uncertainties in N2001 prediction for DM-ISM, especially for galactic latitudes less than 15 degrees. So caution should be made, taking into account the uncertainties on the model while trying to figure out the DM contributions from various sources. So, and the low DM of the FRB has also helped in constraining the mass of the CGM of our Milky Way to be less than 10 to the power 11 solar masses. Okay, so next we explored the host galaxy demographics for FRBs. This slide here shows the highest, lowest and the median values for some of the global properties of the host that we are finding. For example, stellar mass, the star formation and the age of the stellar population. The median value for the stellar mass is 10 to the power 9.8 solar masses. Star formation is about 0.1 solar masses per year. And median value for the age of the stellar population that we are finding is about 5 gigayears. Overall, FRB hosts are massive and they are star forming. Here I present the current star formation rate as a function of stellar mass for 23 FRB hosts distributed in 3 redshift bins. The background data for field galaxies here is taken from the Cosmos survey. And we can see that the FRB hosts lie in the region of star-forming galaxies, but there are some exceptions. So blue here is the star-forming galaxies, yellow is the transitioning galaxies or so-called green valley galaxies, and red color show the red-index quiescent galaxies. So here we also see there is no significant difference between the hosts of repeating and non-repeating FRBs themselves. Another way we can examine is looking at the phase space of the specific star formation rate versus the mass weighted age. Now, specific star formation rate is just the star formation rate per unit mass of the galaxy. So this is basically serve as a proxy for comparing the star formation histories of FRB hosts as compared to the field galaxies or underlying cosmos galaxies. And here we are finding that FRB hosts lie in the densest region occupied for the majority of the cosmos galaxies, which tells us that the star formation histories of FRB hosts are pretty much similar to what we see for most of the galaxies in respective redshift bins. I would like to highlight Alex's Gordon paper for more details, which will be published soon. So these are the latest results for the host demographics. Okay, so from the host galaxy considerations alone, we can rule in and rule out various FRB progenitor models. So first here on the left, looking at the host offset distributions, where the host offset distribution meaning the distance between, or the physical offset between the center of the galaxy and where the FRB is happening in the galaxy. So when we compare those projected physical offsets with those of other transients such as...
Left.
Okay, thank you. So when we compare the projected physical offsets for FRBs with other transients such as short and long GRBs, core collapse supernova, type 1a supernova and superluminous supernova, they suggest that the compact merger events such as the white dwarf merger or neutron star merger, the accretion induced white dwarf collapse and the core collapse supernova, they seem to be more plausible mechanisms for producing FRB progenitors. And also the galaxies which are hosting long GRBs and superluminous supernovas, such as dwarf galaxies, those channels are less likely to be the common hosts for FRBs, as you can see in the plot here on the right. Okay, so I'm on my conclusion slide here. So I think the takeaway point is that majority of the FRB hosts are indeed star-forming galaxies. However, FRBs can come from very diverse local environment. A dearth of FRBs in red and dead galaxies is observed. Like most of them are star-forming and very less are quiescent galaxies. And the current analysis is supporting the young magnetar model for most FRBs, in which their progenitors can form through core collapse supernova. However, there is also a possibility that some of the FRB progenitors could still form through more delayed channels, such as merger of two compact objects. And I will leave it here. Thank you very much.
Okay, thank you very much for very nice talk. So we have minutes for Q&A. So, okay, Tom-san, please.
Very nice result. I have two quick questions. First one is most of your hosts are star-forming galaxies, but is there a possible bias that for the given stellar mass, quiescent galaxies are more difficult to be detected because partly, they don't have emission lines? Is that possible? The second question is, can you say something about the metallicity of those host galaxies?
Thank you for the question. So first, yes, there could be possible biases because our telescopes are not perfect. So I will say, yes, that could be a reason. But as you see, most of the host galaxies, they are coming from the star-forming region. So that currently the evidence is telling us that some events such as core collapse supernova might be more common for producing FRB progenitors. But yes, I agree there could be biases involved here for non-detecting quiescent galaxies. For the second point, the metallicity, they are not very highly metallicity of the host galaxies, and they are not very low as well. So I should have written the mean metallicity number in my slide as well. But yeah, in general, they are not very high metallicity galaxies.
Thank you.
So pretty much like our own Milky Way, I would say.
Any other question from online? Yes, online.
Yes, there's an online question from Susumu. Okay.
Yeah, thank you for the very nice overview. For this FRB above redshift 1, you mentioned evidence of a very large contribution to the DM by the host. But how confident are you of the intergalactic contribution? Could a fair fraction of the excess DM maybe due to an above average contribution from intervening halos or maybe the cosmic web?
Thank you for that question. So this is something that I think Clancy is online, so maybe he can comment. So this is the work of Clancy James. I hope you can see my slides here. So this is how the probability distribution for the DM, the extragalactic DM versus redshift look like. And then what we really use is the McQuart relation. So you have the McQuart relation, so you know approximately what is the IGM contribution that you expect. But yes, that McQuart relation is not very well constrained. There is some scatter in that relation, but even accounting for that scatter, this is the number that we get.
Okay, well, I guess it's a matter of probability, but okay. Yeah, thank you very much.
Is there any other questions from either local or online people? If no, I have a question. Thank you very much for very nice talk. So if I remember previous host galaxy paper, maybe read by you, maybe presented the emission line diagnostics for FRB host galaxies. And then if I remember, emission lines, optical emission lines, BPT diagram indicates actually many of them are located in between, if I remember, star formation or safer times, if I remember. And then could you comment on this new sample about the BPT diagram?
Yes.
Do you
So
have measurements?
I don't have a BPT diagram slide, but I do have, let's see. Yeah, so the difference between those results and this result is that when I compared my sample, I compared it with the Primus survey data. And what Alexa is doing here, she's comparing with the Cosmos data, and that's just because the way that these parameters are determined due to the prospector non-parametric fits, it's pretty much similar. So the way that these parameters are determined in the survey of the field galaxies and in the host of FRB galaxies is pretty much the same. So it's more apples to apples comparison. Whereas in the Primus data, we observed that there was an offset of the majority where the star formation sequence, the star forming sequence for the galaxy was lining. So that's why all these FRBs were slightly offset, because the way that the Primus survey, they calculated their parameters was different from how FRB parameters were calculated. So it was just the difference, and the offset that we saw was just because of how the Primus data and the background data calculated or estimated their stellar parameters. So that was actually a confusion, because we expected FRBs to come from star-forming galaxies, and we initially saw this offset, but now that's reconciled given we are now using the exact same methods done for both the sample, and now they agree.
I see. Thank you very much. Actually, regarding Tomo's previous question, I just wonder if there is a measurement for metallicity for your sample and your host galaxies to compare with the normal star-forming galaxies in terms of metallicity. Can you give some comments on this?
Yeah, so I don't have the exact number in my head, but I can post that and talk about that in the Slack channel if that's okay.
Should be. Thank you very much.
But yeah, we are not finding really high metallicities like what we see in dwarf galaxies, so it's not very high.
Okay, thank you very much for clear answer. We have a little bit more time, so do we have any question? No, I'm sorry, we don't have time. Okay, so thank you very much. So let's thank speaker again.